Hello, students. Welcome back to Thermodynamics Part 6. Okay, so we'll start with entropy today. So, our main focus will be entropy and third law of thermodynamics. So, this is a very important criteria for defining a state, okay, or a system. So, if you think about a molecule, if you just leave it in an open space where no other molecules are present, then it will travel in a straight line. Okay, if they don't suffer any collision or something like that, they will travel in a straight line, and that can be in any random direction. Okay, they may spin like a top, and the bond in the molecule may stretch and compress. So these are the types of say movements a molecule does. So if a molecule is say moving straight, then that is termed as transitional movement. If it is spinning like a top, it is rotational movement. If it is bend, stretching and compressing, it is vibrational movement. Okay, so these are the three types of movement, and this movement motions become more vigorous and entropy increases. So what happens when we raise the temperature, they get enough energy to do this types of motion like transitional, rotational, vibration in a more rigorous way, and this results in increase of entropy. So this is something like that if something is very random, okay, it is very moving very fast, and if it's doing very fast things, okay, so that thing is called as entropy. This is a very basic definition of entropy, which says that it is the measure of randomization. So if you think of randomization, so when a thing will be more random, when it will have more energy, then it will have more randomization. So this is the one criteria. This is one of the criteria that we can put, but there are many more other things that are to be considered. Okay. So on the other hand, if we just lower the temperature, then entropy will of course decrease, right? It should be very obvious that the entropy will increase. Clear? Next. Next is what? Next is your third law of thermodynamics. So keeping the idea of entropy in your mind. So what is entropy? It is basically the randomness with which a object can move. So what are we doing here? So if you just decrease the entropy less and less to a very small extent, then you will find that the entropy of any pure crystalline substance will approach to zero. So as we lower the temperature more and more, it will fall or it will become close to zero. Clear? So at lower temperature, and what is that lower temperature? That is called as 0 Kelvin. Okay, so that is not attainable at all. Okay, although it is not attainable at all, but if it is possible to attain that temperature, then the entropy of any pure crystalline substance at that temperature will be zero, and this is called as third law of thermodynamics. Clear? Now, what is the importance of third law of thermodynamics? So we know that entropy of any substance at absolute temperature is zero. Clear? So we can calculate the entropy of any pure substance with the help of thermal data, because we know that entropy is now a function of temperature. So it can be used if you just vary the temperature, then it can be used to calculate the entropy. So specifically, if I talk about the entropy of a pure substance, then it is done by summoning Q reversible by T. Means all the Q that is being say exchanged reversibly divided by the temperature at which it was reversed or at which it was exchanged. Okay, so we will take the increment from 0 to 298 Kelvin. Okay, what are the increments between 0 to 298 Kelvin? We will all include those. Now, standard entropy can be used to calculate in a standard entropy by Hess's law of calculation. So again, you can use this Hess's law of calculation to calculate the deltas. So this is the third law of thermodynamics. Okay, this is the third law of thermodynamics. Next, what is the criteria for equilibrium? So for that, you have to know about Gibbs free energy. Okay, for that we have to be aware about the Gibbs free energy. So Gibbs free energy means this spontaneity is known with the help of Gibbs free energy. So it helps in the prediction of useful work that could be extracted from it. So more negative the value of this Gibbs free energy, more the reaction is reversible. Okay, so it totally depends upon the sign and magnitude of the free energy, that whether the equilibrium will be same or it will just shift to left or it will shift to right. Okay, clear? So, reversible under strict thermodynamic sense is a special way to carrying out a process such that the system is all time in perfect equilibrium with its surrounding. So, what is the meaning of this? So, it says that when we say that some process is reversible, so we mean that if you are carrying out that process in a reversible way, then the system at all time is in equilibrium with its surrounding. So we do a very small amount of change such that the equilibrium between the system and the surrounding cannot be disturbed. That is the basic idea for reversible reaction. So when applied to a chemical reaction, the term reversible indicates that a reaction can proceed in either direction simultaneously so that a dynamic equilibrium is set up. So what is dynamic equilibrium? The equilibrium which is and under which the concentration may change. Okay, it may change, the pressure may change, anything can change. Means there is a dynamic equilibrium, means the rate is equal, but not the rate is not zero, right? It's the rate of forward and backward is equal, but it is not zero. They are just cancelling each other. So the term reversible indicate that a given reaction can proceed in either direction simultaneously. So that is the reason we put a double headed arrow in some reactions, because it can move in either direction. Clear? Now, this means that the reaction in both the directions should proceed with a decrease of free energy. So this is the very important thing. So if you are saying that it is reversible, it means that it can proceed in both directions. Okay, it has the compatibility of moving in both directions, and now it also means that there is a decrease in free energy. So if you move from along left side, then also the Gibbs free energy value will decrease. If you move along the right side, then also a decrease in free energy will decrease. So in both cases it will happen, and we will say that okay, there is a decrease in free energy. Therefore, the final energy is smaller, and the greater energy and the initial energy is greater. So final minus initial will give you negative value of delta H, which is not possible, because it is not possible that in both direction the decrease in free energy is what it is decreasing. Okay, means the decrease in free energy is positive. So it is possible only if at equilibrium the free energy of the system is minimum. Okay, so this is the only possible way to do so. That how can it happen that the Gibbs free energy is smaller in both directions? So it is only possible when the Gibbs free energy at equilibrium is minimum. If it is not so, then the system will spontaneously change to configuration of lower free energy. Okay, clear? So if something is in equilibrium, so it means that in that state, the free energy is minimum. That is the reason it is being constant at that peak. Okay, but if it is not minimum, it is not the minimum energy, then it will move such that the energy become minimum. Okay, or it will move in such a direction that the reaction becomes at minimum free energy. Clear? So you can think of it as a ball. Suppose a ball is caved on a hill. Now, if you try to stop the ball in the middle of the slope without any external effect, will it stop? No, of course it will roll down and roll down until it's reached the bottom where the depth is minimum. Sorry, where the depth is highest but the height is minimum. So in that way only, if you want to say stabilize or bring something in equilibrium, then it will have to move in a place where the free energy is minimum. Clear? So we can say that for equilibrium, delta G is equals to 0. Okay, so since I have told that there is same decrease in free energy in the either direction, and then only we can call it as equilibrium. So there it means that Gibbs free energy for both reactant and product is 0. So that results in delta G is equals to 0. Clear? So this is the very basic criteria for equilibrium. It should always be in your mind that if you want an equilibrium, then your delta G will be 0. Okay, if you are at equilibrium, then your delta G for either direction it will be 0. Now we know the formula that delta G is equals to delta G naught plus RT ln K. So we know this formula. So we take delta G naught is equals to 0. That brings us to this formula that at standard condition delta G naught is equals to minus RT ln K. So what we are taking equilibrium condition. So in normal condition, this formula is delta G is equals to delta G naught plus RT ln Q. Okay, not K, it is Q. That is reaction quotient. If we take the equilibrium case, then Q will be equals to K and your delta G will be equals to 0. Clear? So this will give you delta G naught value is equals to minus RT ln K. Now if you put the value of ln, it will be 2.303 RT log K. Now we also know that delta G is equals to delta H minus T delta S. We know it. So we'll just equate both of this. Delta H minus T delta S equals to minus RT ln K. We will get this. Okay. Further, for strongly endothermic reaction, the delta H may be large and positive in such a way that the value of K will be smaller than 1 and the reaction is unlikely to form more product. In case of exothermic reaction, delta H is large and it is negative and therefore delta G is likely to be larger negative too. In such cases, K will be more larger than 1. Clear? So what is the meaning of this? So if you are saying that if a reaction is strongly endothermic, that means that delta H value is highly positive. Okay, it is large and positive. So if you just go back here and move here, that means that this value, okay, this value is very large and positive. Okay. Now, in such a case, the value of K will be smaller than 1. Right? It will be smaller than 1. Why it should be smaller than 1? Because since delta H is much more greater as compared to this term and it is positive, therefore it means that this whole value that is being written here will have a positive value. Okay, it means it will be positive. Now, if this is positive, that means that minus RT ln K should also be positive. Okay, it should also be positive. Then how it is possible? So for that, since it has a negative sign here, so therefore RT ln K should also be negative. So that will result in negative resulting in positive. So this is should RT ln K should be negative. Now R and T are already positive because R is what? Gas constant. Its value is fixed. So it is positive 8.314. Now if you talk about temperature, then temperature is also what? It will be always positive. So we are not talking about the degree Celsius temperature. So we are all the mathematics or all the formulas that we solve, we take temperature in Kelvin. So it is impossible to have a negative value of temperature in Kelvin. Clear? We are not even near to 0 Kelvin. How can we move to negative? So this thing is negative. This thing is also positive. So the next thing that is available to be negative is ln K. So when can be ln K negative? When K has a smaller value than 1. It means that our product is formed in less amount. Okay, it means that our product will be formed in less amount. Okay, so ln K should be less than 1. That will result in a negative value overall, and minus will give you positive value. So the reaction is unlikely to form much product because why? Why is it so? Because K is equals to reactant of concentration of reactant at equilibrium by concentration of product at concentration of product at equilibrium by concentration of reactant at equilibrium. Clear? Okay. So this is the one case. What is the second case? So in second case, we are taking an exothermic reaction. Now, if it is an exothermic reaction, that means delta H will be large and negative. So if I'm talking about strong exothermic reaction, that means that this delta H negative will be strongly negative. So it means that this will give you an overall value. What? So since it is dominating, so this will give an overall value of negative. So when this will be negative, when this should be also negative. For that, ln K should be what? ln K should be positive. For that, K should be greater than 1. Okay? K should be greater than 1 and K is greater than 1. That means that your product is being formed in greater amount. Okay. So these are some very important tables. So questions are asked from here. Suppose we have different scenarios, and for each case, we will see that what is the appropriate temperature for the reaction to be spontaneous. Okay. So first case is that delta H naught is negative. Okay, delta H naught is negative and delta S naught is positive. Clear? And delta G naught is negative. So it will be negative in all temperatures because delta H is positive. So if you just go back here, okay, sorry for this. So we were here. So if this delta S is positive and delta H naught is negative, it means that this is positive, okay, and this is negative. Now this whole term will be positive. On a positive multiplied by negative will be negative, and delta H will be negative. So negative will also give you negative value. So delta H will be negative. So irrespective of temperature, what we are taking, because temperature can never be negative, because we are taking Kelvin scale, it is impossible to get a negative temperature. So reaction is spontaneous at each and every temperature. Clear? Second case. So about second case, so what we have done, so we have taken delta H negative and delta S negative. Okay, delta S negative and delta H negative. So if you go back to this equation, delta H negative and delta S negative. So it means that if you take a higher temperature, so since delta S is negative, so negative will result in positive. So we are multiplying this positive value by T. So if you take higher temperature, then that will result in increase of this overall positive value, and delta H will be positive also. So at higher temperature, this will be non-spontaneous, and for lower temperature, it will be spontaneous. So if you take a lower temperature, then that would result in small value of T delta S, and hence small value of small positive value. So reaction will be spontaneous at low temperature, and its opposite will be what? So if you take high temperature, then T delta S value will shoot up, means the absolute value of T delta S will shoot up, and since it has a positive sign against it, that means that delta G will comes out to be positive. Next scenario, delta H is positive and delta S is also positive. So both are positive. So if both are positive, then how the reaction can be spontaneous? If T delta S value is large enough, because T delta S has a, since delta S has a positive and T delta S has a negative sign against it. So if T delta S will shoot up, then your reaction will be more spontaneous. Okay. So at high temperature, we can say that it has a negative value. Okay, at high temperature, it has a negative value, right? Or next is the case. So if you take a low temperature, then T delta S will be smaller, and hence the negative value will be smaller because delta H is already positive. That will result in a positive value of delta G naught. So reaction will be non-spontaneous. Last case is if you take delta H positive and delta S negative. So here, if you go back to the equation, so if this is positive and delta S is negative, so negative will result in positive. So both of these terms will be positive. So whatever temperature you take, that will increase the positive value of delta H only. So therefore, reaction will be non-spontaneous. Clear? What will be the reaction? The reaction will be non-spontaneous at all temperatures. Now, we may expect strong endothermic to have large K and hence can go near complete completion. So we are talking about the previous statement that if it is largely exothermic, that will result in a what? That will result in a greater value of K. So we can say that all this delta G, delta S and K they are just related to each other. So delta G also depends upon S. If the change in entropy is also taken into account, the value of K or extent of chemical reaction will not be affected depending upon what? whether delta S is positive or not. Okay, if K is measured directly to the laboratory, the value of delta G naught and any temperature, we can calculate it. We know it. It is minus RT ln K. Next, next question is calculate delta G naught for oxygen. Okay, so this is for ozone combustion. If Kp for this conversion is given, so Kp is given, we know that we have to calculate a delta G naught. So very simple formula. It is minus RT ln Kp. Okay, so this is mentioned here that delta G naught is equals to minus RT ln Kp. Right, so R value we know it is 8.314. We put this value here. So minus RT ln Kp, instead of ln we take 2.303 log, and that will give you 1,63,000 joule per mole. Just divided by 1000 to get your answer in 160 in kilojoule per mole, that is 163 kilojoule per mole. Next is find out the value of equilibrium constant for the following reaction as 298 Kelvin. Standard energy change at given temperature is minus 13.6. So we have to find the value of equilibrium constant. So we know the formula. Delta G naught is equals to minus RT ln K. We will use this formula only. Okay, we will use this formula. So we know what? We know delta G naught. We know R, it is 8.314. We know temperature, it is 298 Kelvin. We will put all of this to get the value of what? To get the value of K. See, it is solved here. So K log K will be equals to minus delta G naught by 2.303 RT. So we got it as 2.38. So if you take NT log on both sides, that will give you K is equals to 2.4 into 10 to the power 2. Clear? Okay. Now next. At 60 degrees Celsius, nitrogen tetroxide is 50% dissociated. Calculate the standard free Gibbs energy at this temperature and at 1 atmosphere. Okay. So what it is written that at 60 degrees Celsius, dinitrogen trioxide is 50% dissociated. To calculate the standard free energy at this temperature and at 1 atmosphere. How we will do it? So first of all, we know this is the equation for it. So if N2O5 is 50% dissociated, so we can calculate what? We can calculate the mole fraction in this way. 1 minus 0.5, 2 into 0.5 by 1 into 0.5. So initially we will have 1 mole here. So 1 mole will be dissociated into 0.5 mole because 50% is being dissociated. And since 0.5 mole has been dissociated and 1 mole is forming 2 moles, so 0.5 mole will form 0.5 into 2 moles. This will be the mole fraction of NO2 and this will be the mole fraction of N2O4. What about the pressure? So we have taken 1 atm pressure. Okay, we have taken 1 atm pressure. The PV is equals to nRT. We put this formula. We got this. Next, if you got the value of each of this, then we'll calculate Kp, which is 1.33 atm. Now finally use this formula to find the value of delta G naught. Okay, put this formula minus RT and Kp. You will get it as minus 8.314 joule per Kelvin per mole into 333 Kelvin. So final answer is what? Final answer is 763.8 kilojoule per mole. Is it clear? Okay. So with this, we have completed this chapter. Thank you.